Hello, today we're going to cover the topic of linear equations. Linear equations are something we've already been working with and learning the definitions and terminology of, but we want to focus on a particular case where we have a first order linear equation in the variable y. And so what that means is we are going to see dy dx or possibly y prime. We will see y. And the coefficients of dy, dx, and y will both be functions of x. That's going to be that a sub 1 of x and that a naught of x. And to the right of the equal sign will also be a function of x. We learned a couple of forms in the first couple of sections. One of those was the normal form and one of those was the differential form. But now we're going to see this standard form. And the standard form says that dy dx needs to stand alone. There should be no coefficient in front of dy dx. But if there is a coefficient that is in front of dy dx and you end up having to divide by it, then we may have a possible need to say that whatever a1 of x was, it cannot be 0. And so if we're asked about domain restrictions or, figuring out what the domain is, this a sub 1 of x being equal to 0 would cause a restriction, okay? And we'll see this in some examples and how it all plays out. This equation is not separable. And that's one of the biggest things to note about it is that there's no way for us to rewrite all the stuff that is separate from dy dx so that we have a function of x times a function of y. The form is dy dx plus some p of x times y is equal to some f of x. We have a specific method for solving this with regards to first order linear equations. We will learn higher order linear equations, and that's why I keep specifying first order. So the first thing we have to do every single time is we have to get the differential equation in standard form. So that means moving things around possibly, or we may have been given the differential equation in standard form. If there's a coefficient in front of the dy dx term, you're going to have to divide it over to the other terms. And when you do this, make note of any domain restrictions this might introduce. So just for an example, if you were to divide everything by an x to get to the standard form, then you must state that x cannot be 0 now, okay? So that's our first step. The second step is that we have to calculate this thing that is called an integrating factor. It is denoted by mu of x is equal to e raised to the integral of p of x dx. You have to be very careful with this. You have to take the sign of p of x. Notice the standard form says dy dx plus p of x. So if there's a minus sign there, then that minus sign belongs to the p of x, and you would need to bring it in here when you calculate your integrating factor. If you don't, the problem will still work out. It will just work out wrong. This is kind of the frustration with math, is that you can do wrong things and still have things work out. And so there's really no indicator that you did it wrong, other than sometimes you might make the problem much more complicated. So be very, very careful. Know your standard form, that it is dy dx plus p of xy equals f of x. When we integrate for the integrating factor, when we integrate the integral of p of x dx, we do not put in a plus c there. And the reason for that is that if we had a plus c, that would end up being an e to the c, which is just the multiplier of c. So it's just a constant that would go away in the end. And so we don't worry about it. The calculation of the integrating factor could introduce further domain restrictions. Okay, so maybe in the first one I should also say, so if there's a coefficient in front of the dy dx term, you must divide it over to the other terms. And when you do this, make note of any domain restrictions this may introduce. So that's a key part we have to keep our eyes open for at each step. Okay. Once we've calculated the integrating factor, whatever it happens to be, we will multiply both sides of the linear equation by the integrating factor. That's what this step looks like right here. Now, of course, e to the integral of p of x dx will be some function or possibly just a number. And we're going to multiply it by every single term. And what ends up happening is that the left-hand side is actually going to be the result of having applied a derivative to a product. And that product is y times e to the integral of p of x dx. And we'll see this with some specific examples. I feel like this, just looking at this with generic p of x, it's not obvious. And it's not necessarily believable either. So I'll point it out when we get to this part within the examples that we have. Now, once we have our integrating factor multiplied all the way through, and on the left-hand side, we have rewritten our sum of stuff to be the ddx of y times e to the integral of p of x dx, then we're in a position where we have a function of x on the left, a function of x on the right, and so we can integrate both sides with respect to the same variable, x. When we do that, we want to make sure to have only one constant of integration on the right-hand side. So we'll integrate with respect to x and only have one constant of integration when we're done. Once we've done that, then we will solve for y. This typically is very possible. In fact, it's typically very straightforward to do. And then in the very end, most of these problems, if not all of them, ask you for an interval of definition. And that interval of definition is going to come from having made note of all the domain restrictions that came up in steps 1 and 2. Right? In step 1, if we divided by a coefficient in front of the dy dx term and it introduced domain restrictions, that was the start of determining our interval of definition. In step 2, when we calculated the integrating factor, that was the next step in seeing whether we have more domain restrictions. And then the actual solution itself might possibly have some domain restrictions as well. We put that all together and we look at the intersection of all of those domain restrictions, and then we can state our interval of definition. The last thing to do is to determine transient terms. And transient terms, these are just terms which would go to 0 in the limit as the independent variable goes to infinity. So that means we're going to have to examine the limit of our solution to determine if over time any terms just go away. Okay? So as I said before, the best way to see this is for us to go ahead and get started on some examples. So let's go ahead and do that. The first one, we are asked to find the general solution of the given differential equation. We are asked to give the largest interval I over which the general solution is defined. And then they want us to determine whether there are any transient terms in the general solution. So let's get started. First, we want standard form. And looking at this differential equation, it is not in standard form. The x in front of the dy dx needs to be divided through the entire differential equation. When I do that, I get dy over dx plus 2 over x times y is equal to 3 over x, comma, x cannot be 0. Now that we've divided by that x, and I can see it in the two terms, 2 over x and 3 over x, we definitely shouldn't be dividing by 0 at all. The second step is to calculate the integrating factor. With p of x equals, and now I've got plus 2 over x, so that'll be my p of x. Okay, so the integrating factor is mu of x equals e raised to the integral of p of x, which is 2 over x dx. When I integrate that, I get e to the 2 times ln of the absolute value of x, and I'm not going to put in the plus c, okay? Because if I did that, it would just end up being divided away, so there's no need for me to do it. I do need to translate what 2 times ln of x is by using log properties. If I have a multiplier in front of my log, it can be translated to be an exponent for what's inside my log. So this becomes e to the natural log of the absolute value of x squared, and then the e and the ln undo each other and leave behind x squared. Now, there is another domain restriction that came up in this process. We ended up dropping the absolute value bars and coming to this x squared, but in the beginning here, we had this ln of the absolute value of x. And so I need to further restrain and say that x must be positive. I have to choose an interval where I've got definition. I'm going to choose x as positive. All right. Now, the next thing to do is to multiply mu of x equals x squared through the differential equation in its standard form. So we're never going back to the original form. We're sticking with the standard form. Okay, so multiplying an x squared through, I get x squared dy dx plus x squared times 2 over x times y equals x squared times 3 over x. Okay, simplifying things, I have x squared dy dx plus 2xy is equal to 3x. Now, here's the moment where I have to recognize that this left-hand side is the result of having taken d dx on mu of x times y. Mu of x is x squared, and then there's the y. Okay, now let's just check it so that you can believe it. If I take d dx of x squared y, I'm implicitly differentiating. Remember, the y is a function of x, so we're back to our implicit differentiation. The derivative of the first is 2x times the second is y, plus the first, the x squared, times the derivative of y with respect to x, which is dy dx. And that is exactly what the previous line says, just written in an opposite order. Okay, so I'm going to rewrite the left-hand side as d dx of x squared y, and on the right-hand side, I just have that 3x. Okay. Now, because I have functions of x on both sides, I can go ahead and integrate on both sides, but it has to be with respect to the same variable. When we were working with separable equations, the differentials were already there. There was a dx on one side and a dy on the other side. So all we had to do was throw an integral on each side. Now, we have to remember that rule that says whatever you do to one side, you must do to the other. So we're not just integrating both sides, we're integrating both sides with respect to x. So we will integrate both sides with respect to x. Okay, so it's the integral of d dx of x squared y dx is equal to the integral of 3x dx. Okay, on the left-hand side, the integral of d dx with respect to x, this is the fundamental theorem of calculus. And the fundamental theorem of calculus says that if I integrate the derivative, and they're in the same variable, then they undo each other and they leave behind whatever the argument was. So in our case, the argument was the x squared y. So then the left-hand side just becomes x squared y. On the right-hand side, we go ahead and integrate and get 3/2 x squared plus c. And we're almost done. The next step is to go ahead and solve for y. And state the interval of definition. Okay, so if I divide both sides by x squared, I get y is equal to 3/2 plus c over x squared. And my interval of definition from up above, I have this x is positive, so I will put in x is positive. So I've got my solution and I have my interval of definition. The last thing is to state transient terms. All right, so we have to examine what happens in the limit as x goes to infinity. Do any of the terms go away? Because if they do, then that's going to be one of my transient terms. So looking at 3/2 plus c over x squared, as x goes to infinity, 3/2 just stays 3/2. But the c over x squared, as x goes to infinity, that's going to go to 0. So the only term in here that goes to 0 is c over x squared. That means it is the transient term. Okay? So those are the particular answers that are being looked for: the solution, the interval of definition, and the transient terms. Okay? Let's try this again. Let's look to see what happens in question 2. So I've tried to give us a selection of problems that bring up some of the common difficulties that show up. In this one, again, same exact directions. Find the general solution, give the largest interval of definition, and determine any transient terms. All right, so first step is to get into standard form. That 1 plus x that's in front of the dy dx is no good. I need to divide every term by that 1 plus x so that I can get this in standard form. When I do that, I get dy dx minus x over 1 plus x times y is equal to x plus x squared over 1 plus x. I need to notice that this term on the left becomes, if I factor an x out of the top, it's x times 1 plus x over 1 plus x. So the whole thing simplifies to just be an x. So I'll rewrite one more time. Dy dx minus x over 1 plus x y is equal to x. Okay, now I need to integrate this. And in particular, we're going to find the integrating factor using p of x is equal to negative x over 1 plus x. Now, I have a problem right here. I have an improper fraction. I have the same degree on top as I do on the bottom. This is not something that I necessarily can integrate without doing some algebra. I have two options here. I can do long division, I can do synthetic division, or I can do a little trick. I'm going to show you a trick, and in other problems I'll show you long division, but the trick is extremely useful, and so you will want to know this one. Okay, so the first thing I do is that negative that's on top, I pull it out in front and I put some parentheses in. So I still have an x on top and I still have a 1 plus x on the bottom. Then on the top, if I add something onto the top, I'm going to change my entire problem. It will not be the same. But if I add it and subtract it at the same time, then I'm not going to change my problem. So here's what I want to do. I'm looking at the bottom and I see this, that I have 1 plus x. So what if I had a 1 on top? Then it would simplify so much more easily. But I can't just have a plus 1. I need a minus 1 as well. And if I do that, Then what I can do is keep that negative on the outside still. I can rewrite this as x plus 1 over 1 plus x, and then minus 1 over 1 plus x. And now that first fraction simplifies. I still have my negative on the outside. The first fraction, x plus 1 over 1 plus x, those are the same thing. So I have 1 minus 1 over, and I'm going to write the bottom as x plus 1. Okay, so p of x is actually equal to negative 1 plus 1 over x plus 1. So that's what we have to plug into our integrating factor calculation in order to come up with the integrating factor. Okay, so mu of x is equal to e raised to the integral of p of x, which is negative 1 plus 1 over x plus 1 dx. And now I can integrate. This becomes e raised to the negative x plus the natural log of the absolute value of x plus 1, where x plus 1 must be greater than 0. And you know what I forgot to do is in step 1, I should have stated that 1 plus x cannot be equal to 0, which means x cannot be negative 1. All right, now I need to rewrite that integrating factor because that doesn't look very good right now. So I'll rewrite it using my properties of exponents. This is e to the minus x times e to the ln of the absolute value of x plus 1. The e and the ln undo each other completely, and I'm left with an x plus 1 in parentheses times e to the minus x, and x must be greater than negative 1. Okay, so that's my mu of x. I'm supposed to multiply that through the differential equation. So we'll multiply mu of x equals x plus 1 times e to the minus x through the differential equation. And when I do that, I'm multiplying it through this version of the differential equation. Okay, so I get x plus 1 times e to the minus x times dy dx. Let's do minus x plus 1 times e to the minus x times x over 1 plus x times y equals x times x plus 1 times e to the minus x. Okay, now I need to clean this up just a little bit. So this becomes x plus 1 times e to the minus x dy dx minus the x plus 1 and the 1 plus x. Those divide out, and I'm left with minus x e to the minus x times y is equal to, and on the right hand side I have x squared plus x times e to the minus x. Okay, so supposedly this left hand side is the result of the product rule d dx on mu of x, which was x plus 1 times e to the minus x times y. Okay, and it actually is that. So in order to see that, we need to actually take d dx of both sides. And so when I do that, the derivative of the first, I'm going to deal with the x plus 1 times the e to the minus x all together. Okay, so I have d dx of x plus 1 times e to the minus x, and then times y, plus, and then I have x plus 1 e to the minus x times the derivative of y, which is dy dx. Okay, so I didn't actually take my derivative of x plus 1 times e to the minus x. I showed that I need to still. So when I take the derivative of that, what I get, the derivative of the first is 1 times e to the minus x, and then we get plus the x plus 1 times a negative e to the minus x. And when we distribute everything through and combine like terms, this is just going to equal a minus x e to the minus x. Okay, so that becomes a minus x e to the minus x times y plus, in parentheses, x plus 1 e to the minus x dy dx. And that is exactly what I have up above. Now I'm showing you that the result on the left-hand side is coming from a product rule. This is not something you have to show, but I'm doing it to convince you that this is true. This is not something I show in my own work, but I might check it in my head to make sure that it is working out, okay? So in 4, I rewrite everything, and I've got the left-hand side is d dx of the x plus 1 times e to the minus xy. This is equal to, on the right-hand side, x squared plus x in parentheses times e to the minus x. And now we are allowed to integrate both sides with respect to x. So I get the integral of d dx of x plus 1 times e to the minus xy dx is equal to the integral of x squared plus x times e to the minus x dx. Okay, left-hand side is easy. The integral and the ddx, those are going to undo each other by the fundamental theorem of calculus. The right-hand side is not quite so easy. I need to shrink up some of my work. I've been writing a little bit bigger than I normally do. And so I'm just going to shrink this up a little bit so that I have room to finish writing this problem. Okay, so I need to integrate the right-hand side, and it requires an integration by parts, which I call IBP for integration by parts. So over here on the right, I'm going to take care of my integration by parts, and I'm going to use tabular integration because it will be faster. This is a really valuable skill to learn. I teach it in my Calculus 2 classes, but you might not have learned it in your Calculus 2 class. So the first thing to determine is, of the two functions, x squared plus x, and then the e to the minus x, we need to determine which one would be best to have as the u and which one should be the dv, okay? And so I will set this up. So I've got my u and my dv in columns. It would make the most sense if x squared plus x was my u, because as I differentiate it, the powers go down until they go to 0. So in my u column, I have my x squared plus x, and then I'm going to say that to the right of it, I have a plus sign. Okay, so I have to keep track of my signs, because we all know that the integration by parts is uv minus the integral of v du. Okay? Now I'm going to continue to take derivatives of it. The first derivative is 2x plus 1, and then I need a minus sign next to that. And then I'll take a derivative again, and that's 2, and then I need a plus sign next to that. And the next derivative of it gives me back a 0, which is great. And that would be a minus sign next to that. For my dv, I have e to the minus x, and then I'm going to go ahead and just take antiderivatives all the way down 4 lines, just like I have 4 lines for you. So the first antiderivative is negative e to the minus x. The next one is positive e to the minus x. And the next one is negative e to the minus x. Now, we take a diagonal product. This is the uv, right? The first line is u, and the second line in the second column would be the v. So I have my uv, and then I would normally do a minus, and that's where this little minus sign is coming from, a minus v du, but with tabular integration, I'm not going to write out minus the integral of v du. this tabular integration is fantastic because it allows us to collect the 3 integration by parts we would have needed. Okay, so the next step is actually another UV, but the sign that goes with it is right next to the 2x plus 1. So I know I have a minus and then another product. So diagonal slant tells me a product, and then I'm going to get a plus and then another diagonal product, and then in the next row I have a 0. And so now I'm going to go backwards and have my minus v du and be done with this. So when I write it out over here, on the left-hand side of this integral, the fundamental theorem of calculus takes care of things. I have x plus 1 times e to the minus x y. And on the right-hand side, I get, in parentheses, x squared plus x times a negative e to the minus x. And then I have a minus, in parentheses, 2x plus 1 times an e to the minus x. And then I have a positive 2 times a negative e to the minus x. And then I have no more, so I get plus c. And then that just took care of a bunch of integration by parts all at once. Now, what I want you to try to do is do it the old-fashioned way. Do integration by parts several times and make sure that you're coming up with the same thing. And this is more of an exercise to convince yourself that tabular integration works, so long as you do it correctly. All right, so the right-hand side's pretty ugly. I'm going to go ahead and combine some like terms by factoring out an e to the minus x. So if I pull out an e to the minus x, what I'm left with inside is a negative x squared minus x minus 2x minus 1 minus 2. Maybe I should pull a minus out as well. So I get a negative e to the minus x, and inside I have x squared plus 3x plus 3. Okay. Finally, I can solve for y by dividing both sides. Oops, I've lost my c, plus c. Okay, dividing both sides by an x plus 1 and an e to the minus x. And so I get y is equal to a negative e to the minus x times the x squared plus 3x plus 3. All of that is divided by the x plus 1 and the e to the minus x, plus c over the x plus 1 and the e to the minus x. If I rewrite this and simplify it, and the e to the minus x's need to be written upstairs in the second fraction. In the first fraction, the e to the minus x's divide out. Also in the first fraction, the x squared plus 3x plus 3 doesn't factor, so nothing's going to simplify. And my final solution here is going to equal a negative of the x squared plus 3x plus 3 divided by x plus 1 plus a c e to the x over x plus 1. Now, if I look at those terms individually, the first fraction is quadratic on top and linear on the bottom. And so the best I could see is that it looks like I'm not going to have any terms going away. You know what? I do want to rewrite this though, so give me just another moment. Sorry, while I ponder the best way to do this. Just make this smaller. And then I'm going to get my plus c over here. Okay, I want to do one more rewrite because there are actually some things that may simplify, and we want to see if there's like a hidden transient term that we just can't see. Okay, so I have y is equal to, in that first fraction, I'm going to split it up. So I've got a minus x squared over an x plus 1. That very clearly doesn't go to 0. That's going to infinity. Minus, in parentheses, I have a 3x plus 3 over the x plus 1. And then I have a plus c e to the x over x plus 1. The 3x plus 3, a 3 will factor out of there and leave behind an x plus 1. And so that does simplify. We end up with a minus x squared over an x plus 1. That second fraction reduces to just minus 3, plus a c e to the x over an x plus 1. And so there were no hidden transient terms, but now I know for certain. Another way that you could do this is on the x squared plus 3x plus 3. We could have used long division in order to see if in rewriting it we could find some transient terms. But it looks like we're good. We just get a minus 3, and so that's not going to go away over time. None of the 3 terms are going to go away. So my last little statement here in statement 5 is that there are no transient terms. And then I do need my domain, which was x is greater than -1. Okay, so I will box that, and then I've got my no transient terms. Okay, so one last example. In this example, we're asked to solve the IVP, so now we're given an initial value. We also need to give the largest interval over which the solution is defined. But for some reason in these IVP problems, we are not being asked for the transient terms. I'll still look to see if there are any, but we'll see. Okay, so first step is still the same. We need to get things in standard form. But if we look at this, we have y prime minus sine of x times y equals 2 sine of x. My y prime is already totally isolated. So the only thing I would do is just rewrite it as dy dx so that I can focus on those differentials there. So dy dx minus sine of xy is equal to 2 sine of x. Okay, the second thing is to find mu of x. Remember, it's e to the integral of p of x dx. And here, p of x, remember to take the sign, is a negative sine of x. Okay? So this means mu of x is equal to e to the negative integral of sine of x dx. And the negative integral of sine of x is a positive cosine. So this is just e to the cosine of x. And that's it. Okay. There are no domain restrictions that come out of this. We didn't have to divide anything. Sine is defined for all values of x. E to the cosine of x doesn't bring up any domain restrictions either. So far, we have an interval from minus infinity to infinity, so we're good. The third step is to multiply mu of x equals e to the cosine of x through the dE. And what we get is not dy dx. We get e to the cosine of x dy dx minus sine of x times e to the cosine of x times y is equal to 2e to the cosine of x times sine of x. Okay, now on the left-hand side, it should be true that this is the result of having taken d dx on mu of x times y, where mu of x is e to the cosine of x and then times y. So if we were to take the derivative of this product, we would get e to the cosine of x times the derivative of cosine of x, which would be a negative sine of x, and then times y, plus e to the cosine of x times the derivative of y with respect to x, which is dy dx. And looking at that, it is the exact same as the above line, so this is good. All right, so in the fourth step, we rewrite. We have d dx of e to the cosine of x, y, on the left. On the right, I'm going to rewrite this again, 2 sine of x times e to the cosine of x is on the right. Okay, now we can integrate with respect to x. And so we do the integral of d dx of e to the cosine of x times y, and this is with respect to x on both sides, is equal to the integral of 2 sine of x e to the cosine of x dx. Okay, the left-hand side is easy. The right-hand side, we need to think about it a little bit. On the right-hand side, as with all integrals, I always start off thinking, could I do a u-sub? Like that's our easiest method that we know of, and so I always think of that first, and I don't go to integration by parts unless I can't do a u-sub. So if I was to do a u-sub in the 2 sine of x e to the cosine of x, I would let u be cosine, and then d would be a minus sign. And so this will work. So I'm going to do a u-sub. And I'll do it over here on the right. My u-sub work. U is equal to cosine of x. du would be minus sine of x dx. Notice that in our integral, we don't have a negative symbol, so I'll move that over. Minus du is equal to sine of x dx. The 2 can still be there. That's fine. So when I replace stuff in my integral, I'm dealing with the integral of negative 2 and then e to the u du. So when I integrate that, I just get a negative 2e to the u, and then I need to go back to my x functions. So this is going to equal negative 2e to the cosine of x. Okay, well, let's do this. Going back to our integral, the left-hand side, the fundamental theorem of calculus is going to say that the integral of d dx just leaves the argument, e to the cosine of x times y. On the right-hand side, we get a negative 2e to the cosine of x plus c. Then we divide both sides by cosine of x because we need to solve for y. And so y is negative 2 plus c over e to the cosine of x. All right, so this fraction on the right-hand side, the c over the e to the cosine of x, I'm just thinking about it now. We were not asked for transient terms at all, but e to the cosine bounces between -1 and 1. What that means is that when cosine gives us back a negative value, this fraction is going to be big because e to a negative number ends up going to the top. And then when x gives us a cosine that is positive, then the bottom is going to be bigger, and so the fraction will be smaller. So we're going to see a bouncing sort of thing happening. We're not going to see this fraction going to 0 or going to infinity. It's just going to be bouncing up and down, up and down, up and down. Okay, so there are no transient terms here at all. And again, that wasn't asked for. I just want us to think about it each time when we come upon our solutions. What was asked for is to find c. And we're using our initial condition, which was y of pi over 2 is 1. That means x will be pi over 2 and y will be 1. So when I plug things in, I get 1 equals negative 2 plus c over e to the cosine of pi over 2. Cosine of pi over 2 is 0 and e to the 0 is 1. So I get 1 is equal to negative 2 plus c. 3 is c. So finally, our general solution to the IVP is y equals -2 plus 3 over e to the cosine of x. And then we need an interval of definition that was asked for. And as we went through this problem, we'd never had to divide it by anything. So there were no domain restrictions when we went to standard form. The integrating factor introduced no domain restrictions. The final solution never has any domain restrictions because e to the cosine of x is never equal to 0. And so we would say that the interval of definition is -infinity to infinity for this particular problem. Okay, so that's 3 examples covering the linear equation. You have now learned 2 methods, separable equations and linear equations. My advice is that you take some time to write up what is the general form for a separable equation, what are the steps for solving, what is the standard form for a linear equation, and what are the steps for solving. And as we learn more methods, keep writing those things down for yourself, because really this is about remembering what is the process for each type that we work with. If you have any questions in your homework, please reach out for help.